All right, so last time we barely started talking about 6.2 and 6.3, so we're going to continue that. So remember, we're essentially getting this idea of something called antiderivatives, so we're essentially going backwards, if you will. So we've gotten so used to going forwards with derivatives, and now I'm going to ask you to go backwards. And also because I'm going to use them pretty interchangeably because they are, I'm going to be bouncing back and forth between saying integrals and antiderivatives. They're, while technically somewhat different, to calculate an integral, you find an antiderivative. So I'm going to use them, those words somewhat interchangeably, integral and antiderivative, in this class today, because that's how you find an integral. Is the first thing you need to do is take an antiderivative. So last time we ended on this example, which was essentially we were given a function and we wanted to choose which one of the three was an antiderivative. And I said that the way you can check is that if you take the derivative of the supposed antiderivative, it should be what you started with. So the only one whose derivative came out to be 8x cubed was the last one, so that would be our antiderivative. So that was kind of a, here's your choices, pick the right one, but now we want to go ahead and start doing it just from scratch, finding out what the antiderivative is. So what I want to do first is I want to do these few examples where we kind of just think it through. We will have like rules that we're going to write down. We're going to write them down afterwards. Just like we had derivative rules, we have antiderivative rules, but I kind of want to just think through these first five. So remember, we're essentially going backwards. So say we start with 3x squared and I want to find the antiderivative. So I essentially want to go backwards. Well, if you think about what the power rule for regular derivative says, we bring the power down, subtract 1 from the power. I think someone just popped in unmuted. Let's, just in case. Okay. So if we're essentially going backwards, notice when we do the derivative, we subtract 1 from the power. So if we go backwards, we'd want to add 1 to the power. So let's go ahead and start with that if we're trying to do this one. And again, we're just trying to think it through at this point. We don't have the official rule yet. But so I have an x squared. So if I go backwards, I must have come from some x cubed, because that's the only way that I can take the derivative and get an x squared is if I started with an x cubed. Now, I also have this 3 in the front to consider. But remember, to check your antiderivative, you can always take its derivative. So if we take the derivative of x cubed, we do get 3x squared. That's it. I wrote cubed, but 3x squared. So actually, that 3 in the front is kind of already taken care of when we just make it x cubed. So here, our antiderivative, I should say an antiderivative, and I'll explain that in a bit. An antiderivative here would be x cubed. Actually, no, we talked about it a little bit before, so let me do it full out. You know, the person who's accidentally on mute. Here we go. Just in case. All right. What am I doing? Oh, yeah. So got distracted. So remember when we were talking about it the other day, there we go. So we started with, can you think of a function whose derivative is 2x? And someone said x squared, but then you could also do x squared plus 1 or x squared minus 576 or x squared, whatever number you want tacked on to the end. So whenever we're doing these antiderivatives, we always need to finish the antiderivative with a plus c. Because essentially, there's always... Sorry, someone's having trouble getting in. Let me try to help them really quick. So we always need to have a plus c on the end to essentially take care of the fact that there might have been a constant at the end of the original function. So we always need the plus c to take care of that. Sorry, I'm just trying to get this other person in. That's why I'm semi-distracted. So this here, x cubed plus c, would be our antiderivative. Now, again, we're just thinking these ones through. We don't have our official rules yet, but that's kind of how this process kind of goes. We want to try to think about working backwards. Now, I know that if that wasn't a 3, things would get much more complicated, and we'll get to that in a bit. So since that was a 3, it kind of worked out perfectly. If that hadn't been a 3 in the front, then things would be different, and we'll see what changes on that in a little bit. So for the second one, say we start with x to the 4th. So we want to go backwards. We want to find its antiderivative. So if we want to go backwards, we must have come from an x to the 5th, right? Because that's the only way we can take the derivative and go down to x to the 4th. But now if I were to take the derivative of that, I would get 5x to the 4th. Now that's not what I started with, because now I have a 5 that I didn't have before. So the thing we also need to consider is we need to consider a way to kind of cancel out this constant that we have from the derivative if we didn't start with a constant in the front. Now, how do I cancel out a 5? Well, if I had a 1/5 in the front here, if I had a 1/5 and then I took its derivative, the 1/5 would come along for the ride. I'd bring the power of 5 down, subtract 1 from the power, and then my 5 and my 1/5 would cancel each other out, and I do end up with 1/4, which is what I started with. So not only there did I need to add 1 to the exponent, but I also needed to consider canceling out a constant in the front because I didn't have that constant in the front. Again, we'll be writing the official rules down in just a minute, but just trying to think these through a little bit. So that would be our antiderivative, 1/5 x to the 5th plus c. What about, let me erase this power rule over here. What about if we started with 5? What function has a derivative of 5? So what function do I start with such that its derivative is 5? That must have come from a 5x. The only way you can take the derivative of 5 without having to simplify a bunch would be 5x. So this must have come from 5x plus c, because again, if we triple check with taking the derivative of 5x plus c, we get 5, which is what we started with. Now what about e to the x? What function can I write down such that its derivative is e to the x? Well, e to the x is one of those kind of nice ones with the derivative where it kind of stays itself. So it's going to be true backwards as well. Once it catches up with me. That one screen is cut. There we go. So our antiderivative kind of does the same thing. Since our derivative doesn't really change in e to the x, neither does going backwards. And we can triple check by taking the derivative of the supposed antiderivative and figuring out if it's what I didn't mean to box that one then, that's not the answer. Is it what we started with? And e to the x is what we started with, so we're good. Now on this last one has a little bit of trust and believe me for a moment, and I'll explain it when we write down the official rule. But I want a function such that its derivative is 1/x. So if we think back to our regular derivative rules, what derivative rule gave us a 1/x? That came from a natural log, right? The derivative of the natural log is 1/x. So our antiderivative here seems like it'll probably be a natural log of x plus c. Now here's the trust and believe me for just a minute. We actually have to put absolute values around this. Trust and believe me for a minute. Because if we were to take the derivative of this, we'd have 1/x. The natural log just doesn't really do much for that. But that would be our antiderivative there. And again, I'll explain in a second why the absolute values are there. But so this is essentially what we're doing is we're going backwards now. And we don't always have to put that much thought into it because again, we do have actual written rules just like with derivatives. So let's go ahead and write those down now. But hopefully our brains are in the right spot now. Any questions on that before I move on and write the official rules down? Wait a couple seconds in case someone's typing something. Also, if you're typing your questions, you can always like do the little raise hand thing in Teams so that I, stop babbling and wait for your question. But anyway, well, first I need to say this really quick. So the antiderivative rules I'm going to write them down in integral notation. And again, that's because to find an integral, you're taking an antiderivative. So they're somewhat interchangeable. So I'm going to write down all of our antiderivative rules in terms of an integral. Even though we weren't working with integral notations in the one we just did, that's perfectly fine. I can say take the antiderivative of a generic function without having integral notation. So say we had this. So the integral of x to the n dx, which would essentially also be the antiderivative of x to the n. This is going to be x to the n plus 1 divided by n plus 1 plus c. So you essentially add 1 to the power and divide by the new power, which is kind of what we saw in the first two that we just completed. We added 1 to the power, but then sometimes we had to consider kind of canceling out that constant in the front that gets brought down from the power rule. If you like, you can also put that new power as a fraction in the front, if you prefer that, whatever floats your boat. Though this rule only holds when n is not equal to -1. So when the power is -1, we have a different rule we have to use. But if it's any other number besides -1, we use this. I'm going to call this anti-power rule for the sake of referring back to it later. Then we have that essentially the antiderivative or the integral of just a constant. Now I'm going to use k here because we have the plus c's at the end. So if we're taking the antiderivative of a constant, it's going to be that constant times x plus c. Always have the plus c because, again, you never know if there was a constant in the front, because when we take the derivative of a constant, it's 0. So we kind of have to remind ourselves that there possibly could have been a constant in the back of that function. If we have e to the x, its antiderivative is e to the x. And I'm going to list the antiderivative rule for e to the kx. Just like with the derivative rule, this is technically kind of an anti-chain rule, if you will. So this is technically something we call a u sub, which we'll talk about later. But we essentially have 1 over that constant, e to the kx plus c, which makes sense if you think about it, because the derivative was we brought that power down, the constant down from the power. So now we kind of have to cancel it out. And then the last one for now is if we have 1 over x. So remember, this is technically the -1 case, which is why the -1 case is not included in the anti-power rule. This is going to be the natural log of the absolute value of x plus c. And here's why it's the absolute value. Let's say we started with natural log of x, and I wanted to take its regular derivative. I would get 1 over x. But let's say instead I started with a natural log of -x. Its derivative is 1 over -x times -1 because of the chain rule. So 1 over x. So essentially we have two things that gave the same derivative, but their original functions weren't the same. And the only thing that's different is the sign of the inside piece. So that's essentially why we need a absolute value when we take the antiderivative, is we kind of don't know whether it came from the natural log of positive x or the natural log of -x. If that helps you remember that it needs to be there, then great. If you don't like that explanation, then you don't really have to think about it much. Just remember that there's absolute values. But those are our rules for now. We're going to have, well, I guess we only have u sub that we're going to talk about in a couple of days. And then we have a few properties of integrals. Now, just like we had properties of derivatives, I don't remember if I called them properties or not, but you'll kind of see what I mean when I write them down, probably, because we have very similar things for derivatives. If you have an integral of a sum or difference of 2 or more functions, you can essentially split it up and just do the integral of the first plus or minus the integral of the second. Just like with derivatives, how we just had to take the derivative of each piece, same thing here. We'll just have to take the antiderivative of each piece, add them or subtract them together, depending on what we're working with. In case it freaks you out, it's perfectly okay that there's now two integral symbols and two dx's. Because the integral symbol and the dx as a pair are essentially what tell us take the antiderivative. So that's like the antiderivative notation. So whenever I'm saying antiderivative of a function, I need them. So I need them on both the f and the g. Or maybe it didn't freak anybody out and we're fine. Say you have a constant times a function. If you have a constant times a function, that's going to be equivalent as the constant times the integral of the function. So essentially what this one is saying is very similar to what we were doing with derivatives. The constant just kind of comes along for the ride, and then you take the antiderivative of the function. So just like with derivatives, how the constants just kind of tagged along, constants will tag along here as well. So I'll hold on for a minute or so in case people are still writing those down. I know I didn't pause a lot during those. And then we'll do some examples where we're using the rules and not quite having to think it through as much. Couple more seconds. Okay. Let's do some somewhat more official examples. So we want to find the following integrals. So since these, so notice, also remember in 5.2 we were doing them in our calculator. The ones that we can do in our calculator have bounds. Notice that there's no numbers at the bottom and the top of the integral symbol. So since we don't have bounds, these can't be done in your calculator. There exist calculators that can do them, but you're not supposed to use them in this class. So the only ones that you can calculate in your calculator are the ones that have the bounds. When we don't have the bounds, you have to do the antiderivative by hand. So we want to find the antiderivative, and here we have a sum of two things. So we essentially take the antiderivative of the first plus the antiderivative of the second. So we start with 3x. So we want the antiderivative of 3x, so that 3 essentially comes along for the ride. And then essentially what we're left with to take the antiderivative of is technically x to the first, right? So that's essentially an anti-power rule, where we add 1 to the power, so we'll get 1 plus 1 is 2, and divide by that new power. And then we're going to add that to the antiderivative of x squared. Another anti-power rule, add 1 to the power, you'll get x cubed, divide by the new power. And always end with a plus c. If you want, you can rewrite that a little bit to 3 halves x squared plus 1/3 x cubed plus c. But whatever floats your boat. Just like with derivatives, I don't force you to simplify. If the constants are easy enough to simplify, not necessarily in this one, but in one of the next ones, it'll simplify to a nice number. I would say at least do that, at least try to do that. But I'm not a big stickler for simplification, just like with derivatives. So as long as you get the antiderivative piece right, good to go. Like the antiderivative step. If you don't simplify it, it's fine. So just like when we were doing derivatives, I'm kind of just going to keep going after a little bit. So if you need me to slow down, if you have a question, if you whatever, just stop me as we go. And again, if you want to like raise your hand while you type out the question on Teams, so that I stop talking, or at least don't move forward. Right, Caroline. So our rule, or essentially our anti-power rule, is that we need to divide by whatever the new power is. And the reason that essentially happens is if you think about the derivative, regular derivative, we bring the power down. So if we're essentially undoing that, we would need to divide by essentially that number we brought down, if you will. So that's what our antiderivative rule says, is we need to add 1 to the power and divide by it. So in this example, The new powers turned out to be 2 and 3 respectively because they started out as 1 and 2. So if we added 1, we got 2 and 3 respectively. So I have to then take that number and divide the term by it. So, also, you can always triple check your answer. Remember, you can triple check your answer by taking the derivative of your answer. So if we take the regular old derivative of this, we would bring this, so we'd have 3 halves, 2x plus 1/3, 3x squared. And then the c would disappear. So the 2's would cancel each other out. You'd get 3x plus the 3's would cancel each other out, x squared. And this is exactly what you started with in the integrand. So we know that we took the correct antiderivative. So you can always triple check yourself. But that's kind of why the division needs to happen, is because it needs to undo the power being brought down normal derivative. But anyway. So next one we have x to the 5th. So that'll be another anti-power rule. So our anti-power rule says add 1 to the power, so we'll get x to the 6th. But then we have to divide by that new power, so we divide by 6. Always end with plus c. So if you want to write that as a 1/6 in the front, go right ahead, whatever floats your boat. And you're good. Now we have 12t cubed. So the 12 is going to come along for the ride. And just like with derivatives, once you get good at these, and I don't mean that in a condescending way, once you get good at these, sometimes you can see what's going to happen and you can kind of simplify things as you're in your head in the first step. Like I've been doing this so long that I know that that's going to reduce just 3t to the 4th. So I probably wouldn't write out 12 times t to the 4th divided by 4. I would just do the division in my head. But whatever you need to write out is fine. So the 12 kind of comes along for the ride, and then we have to take the antiderivative of t cubed. So that will be t to the 4th. We add 1 to the power, divide by the new power. Always end with a plus c. And this is what I meant by if they simplify, kind of, you should probably try to do so. We can essentially do that 12 divided by 4 to get 3t to the 4th plus c. So just like with the power rule, how at the very beginning I would bring the constant along and then I'd write something like 3 times 2x. And then eventually I stopped doing that and just jumped straight to 6x. If you can see how it's going to simplify right off the bat, you can simplify the constants right off the bat if you can do that. But otherwise, write it out fully by all means. All right. Okay. For the next one, we have q cubed, which is fun to say, minus 6q squared dq. So we need to take, so here again, we have essentially a difference of things. So we're going to take the antiderivative of the first piece and then subtract off the antiderivative of the second piece. So antiderivative of q cubed, we're going to add 1 to the power, get q to the 4th divided by the new power of 4. Minus the antiderivative of 6q squared. So the 6 is going to come along for the ride. We're going to add 1 to the power, so q cubed, divided by that new power of 3, always add a plus c. So if you want to simplify it a little bit, 1/4 q to the 4th minus 2q cubed, because the 6 divided by 3, plus c. And again, you can always triple check your answer by taking the derivative. If you take the derivative of that, you'll bring the 4 down, it'll cancel out with the 1/4, you'll get q cubed, and then you'll get minus 6q squared, which is exactly what we started with. Questions, concerns so far before we move on to some more, I don't want to say interesting, but I don't know, I'm going to say interesting because it's the only word that's going in my brain. I'll wait a couple seconds before we move on, in case people are still writing some down. Okay, so I kind of have to scroll back up. Hopefully you'll have that one and You stop me if you didn't. Whoops. So now we've got 8x cubed plus 1 over x. So we've got a sum thing, so we're going to take the antiderivative separately. So the 8's going to come along for the ride, add 1 to the power, divide by the new power, so we'll get x to the 4th divided by 4. Now we have 1 over x, which is technically x to the negative 1st. So since it's in this case, this is not our anti-power rule. This is essentially the natural log one. So we will have plus the log of the absolute value of x. Don't forget the absolute value. And always end with a plus c. So if you want, you can simplify the constant in the front to 2. And we're good. The next one is our e to the kt rule, if you will. So that 12 is going to come along for the ride. And then our e to the kx, e to the k whatever, was the one that told us that we essentially divide by that constant in the front of the x and then leave the e to the kx alone. So this will turn into 1 over 0.2 e to the 0.2t, always end with a plus c. 12 divided by 0.2 is going to give you 60, if you were to simplify that. Okay. Now this last one does have the tiniest bit of a trick to it. And a lot of people get stuck on it. This is technically 2x to the negative 2nd plus 7. So since it's a negative 2, that is a anti-power rule, if you will. So a lot of people will see something over an x term and think it's immediately going to go to the natural log thing. That's not true. Okay. Now, we do have that it gets a bit more complicated when we talk about u sub, but essentially the thing you want to look for is it a power of 1 or a power of something else in the denominator? So in number 5, it was x to the 1st in the denominator, and in this one it's x squared in the denominator. So the only time it'll be the natural log rule is if it's to the 1st power in the denominator. So here we technically need an anti-power rule. So the 2 comes along for the ride. We add 1 to the power, so negative 2 plus 1 is negative 1, and divide by the new power. Plus the antiderivative of 7, since that's a constant by itself, its antiderivative is 7x plus c. And of course, you can simplify that the tiniest bit by making it negative 2x to the negative 1st. Plus 7x plus c, and if you're fancy and you want to put the x back in the denominator, go right ahead. Questions, concerns before we go on to the next set of questions? I'll wait a couple seconds. Okay. Okay. So far we've been finding these antiderivatives that have plus c at the end, right? Now we can actually find a specific antiderivative if we're told more information, because then we can essentially find out what that c value actually is. So say I want to find the antiderivative using the given value of capital F of 0. Now remember that capital F is usually used to denote the antiderivative. So essentially it's saying find the antiderivative, and the function when we plug in 0 should give you that value. So essentially this is saying if we take the antiderivative of 2x and then we plug in 0, it should give us 6. So this is how this is going to go. So the first thing we still need is the antiderivative. Now, the one thing I'll say about it's somewhat unfortunate. But it's freaking out. I don't know if it's freaking out for anybody else, but it's freaking out for me. The heck just happened? Okay, I'm still on Wi-Fi. That screen is black. Is anyone else's screen black, or is it just one of mine? Because if anybody else has a black screen, I'll need to try to fix it. But otherwise, I'll just keep going. Going once, going twice. No. It's back now? Okay. So yeah, that's what mine freaked out, but one of my screens is still black. So I don't know what's going on there. The one's fine, the other one's terrible. Anyway, so what was I saying? Oh, the coding language I use, it makes the dx like obnoxiously close to the function, so I'm sorry about that. But essentially, once you see a d, that's the end of your integrand. So we're just taking the antiderivative of 2x. So we've got the antiderivative of 2x, so the 2 comes along for the ride. We essentially have x to the first. So if we add 1 to the power, divide by the new power, plus c, this will essentially be our big F of x function. So let's simplify that a little bit. Let's cancel out those 2's to get x squared plus c. So essentially the kind of new part of this is that we now have this value of the function to tell us what that c value is going to be. So this essentially says if we plug in 0, that must be equal to 6. This is lagging a little bit. There we go. Now 0 squared is of course 0, so this just gives us that c is 6. So essentially that means that the kind of exact antiderivative we get here is x squared plus 6. We've actually found what that c value is. So be kind of careful with phrasing, and especially when you're reading questions on like Wiley or so on. If it says find an antiderivative, it means the plus c. So when it has something like an antiderivative, that's going to be plus c language. And if it says the antiderivative, it probably tells you extra information and wants you to actually find a number instead of just putting plus c. So that's why these ones say find the antiderivative using the given value, because it's actually a specific antiderivative and not just a generic one. So if we do another one, so we've got 6x squared minus 2 that we're taking the antiderivative of. So 6, it comes along for the ride, add 1 to the power, divide by the new power. Antiderivative of 2 will be 2x plus c. So we have 2x cubed minus 2x plus c equals big F of x. So the extra piece of information we're told is if we plug in 0, we should get 10. Plugging in 0, essentially those first two terms reduce to 0, so we get c equals 10. So the antiderivative we want here is 2x cubed minus 2x plus 10. Questions, concerns about either of those two? Okay. Now note that in these two specific cases, the value that we were given was actually the c value. That does not always happen. Okay, doesn't always happen. Also, so we're going to do one right now where it's not that. But notice in the ones we're about to do, we're also not given f of 0, we're given f of something else. I also don't want you to think that, oh, well, then in that case, whenever it gives us f of 0, that's when it gives us c. Not necessarily in that case either, okay? So you always do need to plug it in and check. So it doesn't always just give you the c value. You do need to kind of plug that value in and see what c came out to be. Since those first two turned out to just be polynomials, it turned out to be that way since we were plugging in 0, but that's not always the case. So just a lot of people seem to think that that value just gives you the c value, and it doesn't. Now this next one looks kind of gross, but it actually turns out to be a little nicer than you think it's going to be. So the first thing we need to find is the generic antiderivative. That's the other thing. Maybe I should write up there too. Another way they can phrase instead of using an is they might say the most general antiderivative. If you see the words most general, then they mean the plus c antiderivative. So yeah. So most general or an antiderivative usually means plus c. And then if they say the, it means that they actually want the number. And they'll have to give you the information to find it. So here we need the antiderivative first. So since that's 1 over x to the first, that's the one that gives the natural log of the absolute value of x. Antiderivative of 1, well, that's just x. So it's technically the antiderivative of a constant, so it's that constant times x, but 1 times x is just x, so. And now we're told to plug in e. So we have the natural log of the absolute value of e plus c, and that equals 2e plus 1. Now the natural log of e is 1. So we essentially have 1 plus e plus c, whoops, equals 2e plus 1. Solve for c, let's subtract an e from both sides. Let's subtract that 1 from both sides. We'll get c equals e. E. So the antiderivative we're looking for is the natural log of the absolute value of x plus e. Questions, concerns on that? This last one involves some fractions, so the algebra gets a little gross. I'm going to leave that as kind of the first thing we're going to talk about on Monday, because we could do it in 2 minutes, I think, but just in case people have questions on the fraction bits, I'll leave it for Monday. And then we'll talk about, so we're technically done 6-2, like we haven't done this last one, but this is 6-2, and then so on Monday we'll talk about 6-3. I believe I made your homework so it only went up to 6-2, I believe I did that, pretty sure. So you should be able to do all your homework at this point. I might be lying, there may be some 6-3, but I'm pretty sure I made it just up to 6-2. Anyway. So we're done 6-2. It's about finding antiderivatives by hand. So if you have any questions, feel free to stick around for a little bit. Otherwise, feel free to leave. Have a great weekend, and I'll see you on Monday.